after learning how to name alkanes, let's work on concept check on slide number 26. I'm not going to draw that compound, but a model shown on this is slide 26. First, you need to write the molecular formula. So the molecular formula is just the number of atoms with their subscripts, as you did so far for even non-organic compounds. How many carbon atoms? The black balls are representing the carbon atoms. So how many do you count? 7, right? And if you count the blue balls, they will be 17. So it's 16. So it's C7H16. The second part is asking for writing the condensed structural formula. Condensed, when you go from the model to condensed, you put the first carbon, and how many hydrogens do you see around it? 3. Move to the next carbon. How many hydrogens do you see around it? 2. The same for next one, you have a CH and then a CH3 sticking out. We show the CH3, which is a branch, right? It's sticking out. We show it in parentheses, and then you have a CH. You see that the last one, and there's 2 CH3 groups attached to it. I'm not worried about this part because I told you we take it easy and you won't have this at this point, so don't worry about it. Just learn how to write the molecular formula and the condensed formula for the smaller compounds. Okay, after knowing about the first 7 alkanes, from methane to heptane, and the alkyl groups, you need to memorize those alkyl groups and first 7 alkanes. Then let's move towards cycloalkanes. Let's see what is the difference between cycloalkanes and alkanes. What happens when you have a cyclic compound? Cyclic compound like cycloalkanes. So they are obviously alkanes, but they are cyclic. They are in the form of the ring. There is a slight difference between their formula. The formula of cycloalkanes is CHH2N. They have 2 less hydrogens than alkanes. The smallest cycloalkane is this 3-membered ring, because you cannot have a ring with 2 carbons, right? How to complete the octet, how to complete the 4 bonds? Every carbon needs 2 hydrogens, correct? Okay. Now, let's count. 3 carbons. How many hydrogens? 6. What is the difference between between alkane and cycloalkane? 2 hydrogens, because if you did not have a cyclic compound with 3 hydrogens, 3 carbons, you would have 8 hydrogens, right? CH3, CH2, and CH3. Now, in order to bend this compound and make a cycloalkane out of it, you need to remove one of the hydrogens of each of these carbons, because we do not violate the octet rule. We must keep 4 bonds. So the difference, this is the first thing you need to know about cycloalkanes, is that their formula is different from alkanes. The CnH2n, 2 less hydrogens, and they form ring. How to name them? You know how to name, like propane. It's just cyclic. It's not the straight propane, so you just call it cyclopropane. The next, the larger ring will have 4 carbons or 4 members, and each one has 2 hydrogens. So if you had a straight hydrocarbon with 4 carbons, you would have named it as butane. Now you call it cyclobutane. and so on, cyclopentane, cyclohexane. And we don't have a big variety because not all of them are very stable. So let me just show these. And you're familiar with cyclohexane. So on each carbon for each of these compounds, you need 2 hydrogens. Okay? Let's move towards, what else do we have? That's all you need to know about cycloalkanes, right? We are not worried about the sources of alkene and cycloalkanes. You can easily read about them, and they exist in the crude oil in different regions. You know, some parts of the earth are richer in having the crude oil. The next thing you need to know about alkanes, after knowing their structure and their general formula, which is extremely important to know, is reactions of alkanes. We said alkanes, another name for alkanes or cycloalkanes, is saturated. You remember the very first type of hydrocarbon? They are saturated, okay? Means that they have all single bonds. Single bonds. So they do not have any tendency to react, to accept anything. The only reactions of alkenes you have, reactions of alkanes with oxygen, with O2, just like what you do in, well, again, going back to the grilling example or cooking example, when you have, let's say, for example, C3H8, you add it to oxygen, you burn them in oxygen, right? So your products are always, just trying to make it more clear. Okay, your products are always carbon dioxide and water, and depending on the number of carbons, you will get different number of carbon dioxide and water molecules. So 3 carbons, just a simple balancing. 8 hydrogens and 2 here, so you need 4. 3 times 2, 6 plus 4, 10 oxygens and 10. So this is a fixed reaction as far as the products. Whichever alkane or cycloalkane you add to oxygen, it will give you carbon dioxide and water. This is the same for the rest of them, but at this point, just know that the simplest reaction of alkanes is with oxygen. We call it combustion, right? Do you remember combustion? That's the same. That's what happens when you start the vehicle and ignition starts in the gas tank. Then you have a substitution reaction. I just briefly go over it to tell you what's going on in the substitution reactions. You start using the UV lamp. You start using the UV lamp. It's a substitution. Why? You substituting hydrogen with chlorine or bromine. Chlorine or bromine. Like what? Let's say you have methane. What you have on PowerPoint slide, I'm going to make it a little bit more complete. Whenever you have H nu on the arrow, means UV light. So, when you go to organic chemistry course, you will actually use UV light. You will hold it next to the sample, and after a few minutes you will see the sample start changing color. So what happens is that the light is going to, this is the bond between chlorine atoms. The light is going to break it even, and you will end up having 2 chlorine, you call it the radicals. Again, I'm not going into details. You will learn the details every step with the name of the step in organic. So you basically will substitute at least one of these 4 hydrogens with the chlorine. So what happens to the other chlorine? It will form a bond with the chlorine atom. So you can have more than one hydrogen substituted, like you can have more than one, like if you add this again to Cl2 and H2, if you keep radiating the UV light, then you will have 2 hydrogens substituted by 2 chlorines, and the second HCl compound will be forming. Then CH2Cl2 plus Cl2 in the presence of light is going to be CHCl3 plus HCl. And finally, if you have CHCl3 plus, this way you have, instead of CH4 you have CCl4. So you have substituted all the hydrogen atoms by a halogen. So the second reaction, again, it's a substitution reaction. No addition to alkanes or cycloalkanes. Why? Because they're full, they're saturated. How can you add something? If you're full and you're not hungry, would you like to eat something? No way. The same. Alright, you're done with just the structure of alkanes and a little bit about their reactions. Basically, alkanes, because they are full, they cannot have, they're saturated, they cannot have that many reactions. But let's move towards unsaturated compounds, which are called alkenes. CnH2n is the formula, 2 less hydrogens. Their formula is very similar to cycloalkanes. Why? Because there is a carbon-carbon double bond. If you compare it to a carbon with in the alkanes, in order to form a carbon-carbon double bond, you need to remove 2 hydrogens. So in order to form the double bond, you need to remove 2 hydrogens. That's why you eliminate it from the formula. So alkenes contain a double bond. On the double bond, you know it from Chem-1. One of the bonds is called sigma, another one is called pi. For another type of unsaturated hydrocarbon, you call them alkynes. Cn, even 2 less hydrogens than alkenes. CnH2n minus 2. Because in order to form a carbon-carbon triple bond, which exists in alkynes, we need to remove 2 hydrogens. So 2 hydrogens means 2n minus 2. And here you have 1 sigma bond, but how many pi bonds? To learn these well, in alkanes, and if I put alkanes here again, Cn H2n plus 2, just try to work on these a lot. The only bond you will find it is sigma. So in alkanes you only have the sigma bonds. In alkenes you have double bond, which is composed of a sigma and a pi, and in alkynes you have 1 sigma and 2 pi. In any case, you always have just 1 sigma, and the rest, whatever it is going to be pi, and you don't have more than triple bond. So these 2, alkenes and alkynes, are called unsaturated hydrocarbons. You had them at the very beginning of this chapter. So, for alkenes, The structure for alkanes was very easy and straightforward because all the bonds were single bond. For alkenes, you might have, and for alkenes, remember, you just have constitutional or structural isomers for alkanes. Constitutional isomers. For alkenes, instead of, besides the constitutional isomers, you have also geometrical isomers. So not only the arrangement sometimes changes, but sometimes the geometry, the orientation of atoms is different. Like what? Like cis and trans. I told you the terminology, get used to it. It's a little bit different from inorganic chemistry. Like for example, let's say we have this alkene. We said alkenes contain a double bond, right? So in order to, we get to the point of drawing their structure, okay? Don't rush. I'm just working on the geometrical isomers now. Again, each carbon must have 4 bonds, must have 8 electrons, have a complete octet. So we have, you see, when we have a CH and we don't have the complete octet, you see 1 and 2 more with a double bond. So sometimes you have it as a geometrical structure if you need to find out the geometrical structure. In alkenes, the sensitive part is this on these carbons, on this double bond. Okay, so how do I determine the geometrical isomers? How do I have the different orientations? How do I have it? Put the carbons of double bond first. We are assuming that we don't know anything about the names. Put the carbons, only carbons, okay? Put the groups that are attached to the first carbon of double bond first. What is connected to this carbon? 1 hydrogen, 1 CH3, 3, correct? 1 hydrogen, 1 CH3. What is connected to the other carbon? A hydrogen, right? Because I could have drawn them like hydrogen and hydrogen. 1 hydrogen and a CH2, CH3. So one more time, if I want to draw the geometrical isomers of an alkene, I first put the carbons of double bond, and then I put the rest of the atoms on each carbon of double bond. On the carbon on the left side, there is a hydrogen and there's a CH3. On the other one, you have another hydrogen and a CH2, CH3. Now, how to determine the geometrical isomers? You see a hydrogen and a hydrogen, right? We go by the hydrogens. When you see hydrogens on the same side of double bond, they're both on the top side, right? You call it a cis isomer. The same side, it looks like a bowl, so you call it cis. Hydrogens on the same side. But you could have, after you draw this, you could have had hydrogen on the bottom, right? We didn't say where to put what. Hydrogen here and CH2, CH3 here. Correct? We didn't say what to do. We just said put the groups around it. Now you see hydrogen on one side and this hydrogen on the other side, the two sides of hydrogen. Now you call it a trans isomer. So that's what I want you to learn at this point. Cis and trans isomers are geometrical isomers for alkenes. We call them cis and trans. How to determine them? If you have a condensed formula, a simple condensed formula, you put the carbons of double bond first. You put the groups just random, whatever you want. Hydrogen on top, CH3 on the bottom, or CH3 on top, hydrogen on the bottom. And then the second carbon, the same. If the hydrogens happen to be on the same side, either on top or both on the bottom. We just say on the same side, I didn't say on the top or on the bottom. When the hydrogens are on the same side, we call them cis. Then if hydrogens are on the opposite sides, you call them trans. How do you know if you have a cis and trans geometrical isomers? You must have, for having the cis and trans geometrical isomers, you must have one hydrogen on each carbon of double bond. So first of all, cis and trans is only for alkenes when you have a double bond, but not on every double bond. You must have just one hydrogen on each carbon of double bond. I give you another example to make it more clear. Let's say you have this compound, CH3, CH, CH2. Okay? We don't know the name. We don't want to know the name at this point. So what did I say? Put the carbons of double bond first. What do you have on this carbon? Two hydrogens, huh? What do you have on this carbon? One hydrogen and one CH3. Is it cis or trans? What is the criteria for cis and trans? Must have only one hydrogen on each carbon of double bond. How many hydrogens do you see on each on this carbon? Two, right? Not one. So not cis or trans. You cannot assign cis or trans. But if you have this compound, CH3, CH, CH, CH3, then put the carbons again. One hydrogen. Let me put hydrogen here because I don't want you to think that hydrogen always goes to the top. You can have hydrogen here, CH3. You can have this hydrogen here and CH3. Do I have one hydrogen on each carbon of double bond? Yes. I see one hydrogen here on this carbon and one hydrogen here on this carbon. Hydrogens are on the same side, so what do you name it? Cis. If you change, let's keep the groups here the same. Methyl group on top, the CH3 on top, and let's switch hydrogen here and CH3 here. Do we have hydrogen on each side? I'm still working on the same compound. Yeah, but hydrogens are on the opposite sides, so we call it trans. So you see, cis and trans or geometrical isomer is specific to alkenes so far, okay? We don't have it for alkenes, we have it for alkenes. And now, how to determine them? If the hydrogen, first of all, they must have one hydrogen on each carbon of double bond. So if you're supposed to pick this cis and trans for among some compounds, you look for the one that has one hydrogen on each carbon. So, excuse me. So you will pick the cis and trans. If hydrogens are on the same side, either on the bottom or on top, they're called cis. If they're on the two opposite sides, you call them trans. About the reactions of alkenes, I am not going to ask you for every single hydrogen, every single reaction, sorry. I am just going to work on, you have, like you see on slide number 36, you see Oxidation reactions, let's leave them for organic chemistry. With oxidation reactions, you have change of color. Let's work only on addition reactions of alkenes. Addition reactions of alkenes. So you are adding two double bond addition reactions of alkenes. Assume you have this alkene CH3, CH2 plus HBr. You are going to add hydrogen and bromine to where? To this double bond, because double bond can accept the atoms and change to single bond. So you have two ways. Either add hydrogen to this carbon and bromine to this carbon, or vice versa. Hydrogen to this carbon and bromine to this carbon. So let's draw both of them. If first bromine will be added to this carbon and hydrogen will be added to this carbon. And you see, by adding the two more atoms, you can't have double bond anymore, because you still need to keep 4 bonds around each carbon. And you said, I'm sure you said, what if we add hydrogen here and bromine here? Cannot hear you, but I'm sure you said that. Hydrogen here. A Russian scientist called Markovnikov worked on the products of these types of reactions. He realized that the major product, more percentage, is the one where hydrogen will be added to carbon that already has more hydrogen. So the Russian scientist Markovnikov came up with his own rule, Markovnikov's rule. In addition of hydrogen chloride or hydrogen bromide to an alkene, hydrogen is added to hydrogen rich carbon. So we say rich gets richer, right? That's the rule. It's an unfair rule. So hydrogen will be added to hydrogen rich carbon. Then if you're supposed to pick the product, you will always choose the product that has hydrogen added to hydrogen rich carbon. Yeah, that's all you need to know. Let's work on one more example to make sure you got it. Let's say I have this H2, CH3, right? Is the octet complete on everything? Yes. Instead of HBr, let's work on HCl, because I told you in addition of HCl and HBr. HBr is better than you will see in organic chemistry, but let's see. According to Markovnikov's rule, first of all, you are adding hydrogen and chlorine. According to Markovnikov's rule, hydrogen will be added to hydrogen-rich carbon, right? Because this carbon has 2 hydrogens. How many hydrogens does this carbon have? Nothing, so chlorine will be added to this. So you will choose the compound, which is CH3, CCH3, Cl, and that's CH3. Okay? So that's the product of this type of reaction. That's called Markovnikov's rule. And for alkynes, I just introduced the structure of alkynes to you because I don't want you to be worried about the reactions. Reactions of alkynes is very similar to alkenes, but you need more more material. Alkynes, you remember we said their formula is CnH2n minus 2, and they are unsaturated, and you have a carbon triple bond. One of them is sigma bond, and two of them are pi. Okay, and they are more sensitive. So if you want to like write down a formula for an alkyne, how do you write it? If you have two carbons, 2 times 2, right, minus 2 is C2H2. So that's how you write the formula. I'm not going to ask you about anything about the reactions or any other thing. Just know that these alkynes are even more reactive than alkenes because now they have 2 pi bonds to saturate. Okay, I'm going to go over aromatic compounds and then naming the compounds and a little bit about the functional group in the next video. Make sure you have enough practice because we need your knowledge for the rest of this chapter.